lived in Richmond at the time. I was going to high school in Highland Springs, Virginia. My dad was from Hampton, and he had a number of old school friends that were working out at NACA and eventually NASA after 1958. And they talked highly of the NASA Apprentice School, which was an educational program where you get hired to learn a trade and get paid for it and get an education and a career. And it sounded pretty good. My family wasn't well off. I applied for college and was accepted at VPI, but I don't know, some things looked interesting at NASA. Started here in September 29th of 1961 as a dynamic model maker apprentice. And I was introduced into a small group of technicians working on really neat models of aircraft, spacecraft. We built models for the spin tunnel, which is a vertical tunnel that's used for doing spin research. We built models for the dynamic stability branch, the 30 by 60 full-scale tunnel. And we built drop models, which were robust models of, at the time, Mercury and Gemini Apollo capsules, as well as usually military aircraft, fighters predominantly, that were taken over on a helicopter to Plumtree Island and dropped for spin recovery testing, and then were recovered with a parachute. And it was fun. We were doing a lot of work in balsa wood and fiberglass, mostly wood and fiberglass materials. We did very little metal work. We had engineers would bring drawings for a model, and they'd bring over periodically. They'd come in the door with bags of little Ziploc bags of all kinds of various parts that they had machined, and we would introduce those into the model as necessary. The group had developed techniques for doing very nice models in fiberglass, making molds, first making patterns and then making molds from the patterns, and then making a fiberglass part in the molds that they made. And in order to save weight on their models for full scale, we typically infused a dye, a blue pigment into the resin, so we didn't have to paint it, so we could save weight on paint. The shop was referred to as the dynamic model shop to separate it from the other two model shops on the center that were located at the time in the west area. One was the models and plant structures, and they did a lot of inflatable things. And the other shop was the old west model shop, which derived from the old prop shop that was built back in the, I guess, 20s or 30s to build wooden propellers for wind tunnels. By 1961, it was somewhat new, but not cutting edge at the time. Those techniques had been developed probably as far back as during the war. World War II, for instance, the British built an airplane out of plywood by laminating thin layers of wood in a mold or over a mold with a resin to bond it together, because they didn't have metal. And they made a number of airplanes had wings that were made this way because it was strong, lightweight, and it didn't require aluminum, which was in short supply during World War II. The shop that I was in did develop a lot of neat techniques for doing models this way. We used, in some cases, we used a vacuum to press the fiberglass laminate and resin into a very thin, and trying to get as much resin out of the laminate as possible, because the resin doesn't offer any strength. Its basic purpose is to bond the layers of fiberglass together. And once you have enough in the weave to hold the layers together, any excess resin is just extra weight. And the models that we built were not just geometrically scaled, but they were dynamically scaled, which means that not only was the shape the correct shape, but the weights and the moments of inertia. In other words, a model has inertia, and when you start a model or anything moving, it wants to continue to move. So we have to build the models lightweight, and then we add weight to the wings or the tail to create the proper inertial movements when the airplane is in motion, because a spin model has to be free flying. It has to fly just like the real airplane. And the same thing for the models that we built for the dynamic stability that were flown in a 30 by 60 wind tunnel. They're not mounted on a sting. They're actually suspended from a cable and an umbilical that carries electrical wires to operate control surfaces, servos and motors and so forth. Spin models take a terrible beating, because when an airplane is flying, you have lift, which causes it to go up. Well, when you put an airplane in a vertical wind tunnel, the air is going up, so the model wants to fly downward. And you got it spinning, and then when it recovers, it stops spinning and it wants to fly. And when it tries to climb, the motion is to climb toward the tunnel wall, and we have impact with the wall, so they get beaten up pretty badly. We spend a lot of time repairing models. Sometimes we are able to take the broken pieces and put them back together. Sometimes we have to make some new pieces and replace parts. We'll replace a wing. They stuck an airplane in the ground one day, and they couldn't get it. It was just sticking in like an arrow, and they couldn't get it out. So they got a saw and sawed it off flush with the ground and brought the rest of it back to the shop. We put a new nose on it. And early recoveries were not as common, and that's what the chute was for. It was intended to arrest the spin and recover the airplane. As they learned how to initiate the spins, because every airplane is different, and so you go through a prescribed set of commands, maybe full rudder, full aileron, elevator down, or elevator up, right rudder, left aileron, whatever the controls, the combinations, and you find out what causes spins, and then you start looking at, now we know how to make it spin reliably, now how do we get it back? And so then you go through this whole process again. It's a lot of repetition, and it's flight after flight after flight, and but eventually you find what this configuration can be, how it works, how it reacts. Sometimes the engineers will then change the configuration. They might change the horizontal tail location or the rudder location. Some of these military airplanes are notorious for flat spins, which is a very different type of spin than the typical spin you see at an air show, where an airplane is going down, nose is fairly steep. Flat spin, the airplane is nearly horizontal, but it's spinning, it's rotating, and you don't have a lot of forward speed to get airflow over control surface, and it becomes very touchy getting an airplane out of a flat spin. There's a lot of pilots have died in flat spins. Later on, we took the same outdoor technology and we applied it to general aviation aircraft, and we did a long study of we didn't use drop models for this. We used RC model airplanes, and we used a full-scale airplane, and we used models in the spin tunnel to correlate the process of what are the effects of flat spins on general aviation aircraft, because a lot of young pilots get injured or killed in light planes because the airplanes don't have spin, that they're not spin resistant. And if they get in a flat spin, that's really not much, particularly at low altitude, and that's where pilots get into trouble. They're coming in for a landing and they get upset by the wind or whatever, and they get in a funny attitude, and the spin develops, and at 1,000 feet you don't have any help. So the idea was to provide some information for the manufacturer. If you're going to build an airplane like this, you need to think about doing this to prevent the airplane from spinning. Not how do we get out of it, how do we prevent it? It's a two-way street. We get information from the engineering staff, from models engineering, for instance. And the term engineer, my thought, 18 years old, the guy's an engineer, he comes in, he's got a drawing. Well, what I found out later on, that a lot of these guys are engineering technician, draftsmen, designers. They're not actual engineers. Now, there are engineers in the group, but not everybody there is an engineer. And a lot of those people came out of the shops. Every year in the Apprentice School at this time, they would take a select few and they would give them an extra year of training, and they would move them into an engineering position. And if they wished, there was incentives for them to go to college and get their degree, but they didn't. Not all of them had degrees. But so they came from a lot of the engineering personnel came from the shop people. So they learned how to build, and now they were able to draw and design using the knowledge of how it's done in their designs. And when we come up with a new idea, we pass it to the engineering people. Hey, what do you think about this idea? Can we do this? And we we developed some techniques, we developed some materials that we routinely used in our models that were developed because of an interaction between the engineering and the model builders. Back in the earlier days of this particular shop, they were attached to, in addition to the full-scale tunnel and the spin tunnel, they were also attached to, we had two towing tanks at Langley. They were long. One of them was, I believe, a mile long, and one was a half a mile long. And they were built for studying seaplanes, because back in the late 20s and 30s, seaplanes were a big thing. And they were design and refine seaplane hulls. Well, the Navy had taken over the 1 mile Tank 1. NASA still used the shorter Tank 2. And during World War II, the tanks they studied torpedoes, they studied bombs, they studied ditching. How do you ditch a bomber and have the crew survive? They did studies in the tow tanks with B-24s and B-17s, and then they took a full-scale airplane out in the James River off of the Newport News and ditched it to prove their techniques. Those models were built of balsa wood primarily, covered with real fine silk, either from, a lot of it came from Japan and from the Orient, but they would cover them with a silk fabric and a lacquer-like material to seal it, and were finished very nicely with fillers and lacquer and so forth. And over the years, the balsa stayed around. The little bits of spruce and pine stayed around, and the fiberglass began to take on more more of our building time. We still built some balsa parts. We used balsa structures inside our fiberglass models. For instance, you might have a horizontal tail on an airplane for the full-scale tunnel for a free-flight model, and it may be a fiberglass skin. It may be very, very thin. It may only be 10,000th of an inch thick, but inside that skin would be a structure of spruce spars and balsa ribs to keep its shape while it's being tested. And then where you needed a harder material, spruce and pine would take over for places where you had hinges or mounting some kind of mounting for the part to where it mounts to the fuselage or to the tail. Most of my experience has been with the models out of the model shops that dealt with wood and fiberglass. I did later in my career get to work with some metal work. For our studies, for our work, we used we'd make metal templates. They'd bring us templates, or we'd lay out templates and file them to shape, and then we'd stack them into chunks of pine, and then we'd take tools and shape that and finish it. That would become our pattern for a mold, say for a fuselage or a wing. The technicians and engineers at NACA, this has been many years ago, had developed a really neat tool for doing airfoils. And the machine shop had a beautiful one that they made up for doing metal airfoils. And because an airfoil is a smooth shape, and to do it properly, particularly if you've got something that's tapered, it's the same shape all the way out to the tip, from the root to the tip, but it may vary in chord. It also may vary in shape. It may be a different airfoil shape, overall shape at the root than it is at the tip. Somebody came up with a bright idea. If we have a constant chord wing, airfoil shape, if we had a device, a template, and a thing something that would follow that template and keep a tool like a router bit, keep it perpendicular or normal to the curve, and we had a track that we could run this thing on with a motor to spin it, we could make airfoils fairly accurately. So they developed this. The machine shop had it with a machine tool, and the model shops built them out of a plywood and spruce arm with a track and a mount that had ball bearings on it and a good old electric router mounted to it, and an arm with a little pin on it at the back that had a ball bearing at the in line with the bit, and this pin on an arm that was we knew the distance to the pin and its relationship with the router bit. And the engineers would get their computers, and the computers of the time were the ladies with the calculators in the room that generated all this information, and they'd give us coordinates for the template that this thing could follow, and we could make airfoils really accurately. And by using templates at both ends, we could get we could do tapered wings, and this preceded the idea of what we consider today the optimum method of doing it is, of course, with CNC work. But this is back in the I don't know when this thing got started. I really have no idea, but I would assume it may have started back during the war or maybe earlier. But we refined it pretty far and used it for many years. At the time, we had kind of political agreements between the metal people and the wood people that they don't do wood and we don't do metal. And researchers are always wanting something yesterday. They never want it tomorrow. They always want it yesterday. And metal models take a long time to make. And somebody figured out that if we put enough wood on a piece of metal, we can call it wood and do it quick. So we would make a slab of aluminum and glue some mahogany on top and bottom of it and put it on a table and get our router out, and we'd make these airfoils, and you'd see this aluminum wing with this little slab of mahogany on top and bottom. And but we could get something out quick that they could throw in a 16-foot tunnel or a 12-foot tunnel and say, yeah, that looks good. And then they could go to the machine shop and say, I need one of these, and I need it such and such, and they'd make it out of steel, and they'd have a nice fine model. But they can't afford to do that and keep making changes to it. So we could make something quick that they could make changes to, and then when they got what they liked, then they knew what they needed to get made in a better way. So we did a lot of that. And we found that we could make castings. We had a foundry here, a nice foundry. And they could make a bronze or aluminum casting of a model, and it would be fairly quick compared to machining a model. But metal shrinks when you cast it, so you got to make the pattern bigger so that when it shrinks, it's the right size. But then it's rough, so it's got to be finished. So it's a lot of work. And one of our technicians came up with a great plan. Let's make the pattern the actual size, and then we'll cast it, and it shrinks. So now we take the shrunken metal casting and we put it in, we make a mold off the pattern, a fiberglass mold. We fit the casting in the mold. We make sure that it's undersized all over. And we put some little blocks of something, little wax or something they can put in there to make sure that the casting stays centered in this mold. And they seal up the edges, and they pour very, very thin epoxy resin into the mold cavity, which now encapsulates the metal model, but the outside surface is the shape they want. They can take this, put it in a wind tunnel, and do a lot of rough studies on it before it deteriorates, but they can get information. Again, this is the shape we want to have made for a full model. They may make 10 of these things before they find the shape they really want. Today, it's all done in CFD. The computer has revolutionized model building. They don't need us anymore. They can do it in the computer. You don't find model building is a craft, and it's an art. Back in the day, NACA actually got model builders from where else? From model builders. They went to model clubs. They went to contests and recruited model builders to come to Langley to build models for the wind tunnels. If you were a model builder and you entered a couple of contests and placed somewhere in the top whatever, you could use that as credentials to get a chance to take the exam to come to the Apprentice School. I built a lot of models in my youth, but mostly plastic display models, not flying models. But I took like 2 or 3 years of mechanical drawing and engineering drawing in high school. That was my key to get to take the exam to get to the Apprentice School. And even today in the model airplane world, you don't find a lot of craftsman model builders. They're assemblers. You buy a model airplane kit, you spend $1,000 for a sailplane kit, and you glue the two preformed wings together, mount your radio, and go out to the field and fly. So you don't have to be a model builder anymore. So we become, we don't have the skills available to do things the way we used to. We don't have really the need for it. We don't have that many model builders or model technicians on the center anymore. There's a few. We have a machine shop with some very capable people. We have a metals fabrication facility here. I haven't been in there much lately. That's because of security. A lot of the doors are locked and you just can't walk in anymore. But they have some tooling there that is kind of revolutionary. You think of a 3D printer, a simple thing I've got one at home. I can make parts for my amateur radio assembly stuff, little odds and ends, little pieces here. They do it with a weld, like a TIG welder and a computer, and they start with a flat plate and they could build you a chair or a model or whatever they wanted to do. I understand there's research in some countries to building buildings with 3D printer technology, with concrete slurry and a machine that automatically feeds in the rebar and build buildings. I don't know that we have the capability here to do this kind of work anymore, or we even have the necessity. Back in the 80s, when the model shop got its first CNC machine, and we started doing a lot of our own work for things that we used to get from the machine shop we could do in-house or do in the shop. We very quickly said, okay, let's stop making patterns and molds. Let's make molds. We'll just machine a mold and then go straight to cut out the middleman. Then we started looking at, why don't we just make the model? And we made an RC model for free test for free flying out of foam. Covered it with fiberglass and took it out and flew it. We made a spin tunnel model out of very high density foam. The research still goes on. They still use the spin tunnel. 30 by 60 is gone, sadly. A 16 foot is gone. 12 foot is gone. 4 foot's gone. All the tunnels. We have very few tunnels left. The NTF is probably our mainstay. And we still have some high-speed wind tunnels here that do some very specialized work. But the low-speed stuff is pretty well kaput. Back in the old days, it's still used. The techniques are still there. You go back to the beginning of the airplane, and airplanes were built out of steel, aluminum, wood, a lot of spruce, because it's lightweight and strong. It has nice straight grain and it's strong and it's lightweight. And they'd build wing ribs. Sometimes they'd cut them out of material. Most of the time they were strips and little webs, and it was very beautifully done. The techniques were quite elegant in appearance, and because they needed to make so many of them, they made fixtures for it. And so they just cut up a bunch of wooden strips, and they take like we would build a model airplane, and they'd lay the little strips and glue them together. They put little plywood corner braces on gussets on all the joints and make it nice and rigid. And they'd mount these on a spar, and then when they got done, they'd make a fabric sleeve and put over it, and then they'd stitch the sleeve to the ribs, and then they'd use a material called aircraft dope, or it's a lacquer type material, and you spray that over or brush that over the fabric, and it would dry, and it would shrink the fabric tight and become airtight, and it would make an airplane. You take steel tubing and spruce, and you do the same thing for a fuselage, and you got a Piper J3, or a Liberty, or a Jenny, or a Waco, or whatever. Well, during World War II, we needed men, we needed people. The shops were running 2 and 3 shifts, and we needed people, and they hired a lot of women in the shops. That was the first time, and after the war, a lot of it went out. But we kept at least one. When I came here in 1961, we had a seamstress in the shop, in the West Model shop, and she did all sorts of neat little things for all kinds of projects. She made tool bags for the hangar. She made a lot of parachute harnesses and straps, and for a lot, because we used a lot of parachutes. I mean, not only the flight crews would have parachutes for their testing, but we developed the techniques of using a parachute for spin recovery. We determined years ago that an airplane in a flat spin, if you deploy the right size parachute with the right size shout lines, you could arrest an airplane spinning. So she made all kinds of harnesses and straps, and she got her start making the sleeves for wings and so forth. But she worked here for many years. I'm not sure that I can remember when she retired. It had to be maybe as late as the early 70s, if not later. And her husband worked out here. He was in research on the lunar lander landing, the part of the project. They were doing studies on landing the lunar lander. They had a kid's sandbox that was full of real fine pumice to simulate what they thought was the dusty conditions on the lunar surface. And they would tow this little carriage on the tank carriage, and then release it so that it dropped into this sandbox. And they had little struts with what would normally be shock absorbers. They had nichrome wire that was measured, and they could determine the loads, how much force was exerted on the legs from how much the wire stretched when it landed. I guess it was late 80s. I got an opportunity to fulfill a position that was open in a facility that worked on classified projects. And I don't think I can talk about the projects, but I will make a statement about the concept of what we were doing. They took a group of model builders and machinists and fabrication, metal fabrication, instrumentation. We put us all together in a facility with the designers, and we were a self-contained model building facility. And the researcher would bring a model in, we got the guys together to talk about it, and we, for the only time that I can remember in my career, we had very efficient communication between all the various trades. There was none of this, oh, that's our work, that's your work, this is my work. It was, we got to get this done, and let's get together and go do it. And it was fascinating to watch the machinists come over and say, hey, we need something done on this. You guys, this is your kind of work. So they come over and they do this little part of it. And they said, okay. And then the machinists would go back and work on it. A lot of it involved some really intricate setups where you had to take a model and you had to put it on a table in a configuration so you could get it on a machine and make cuts in the metal. Because most of our output was metal, was stainless steel for wind tunnels. Occasionally we did stuff for like the antenna ranges or other things that used foams and some fiberglass stuff, but a lot of the work was metal. And but we had guys that knew how to support a model and kind of mold it into place so that it would be sturdy and stable so they could machine on it. And then they'd take it apart and they do have to do it all over again upside down. But it was a great opportunity to get the various techniques and trades working together for a common end, and it was a real achievement, and it's a great idea. And I wish they expanded it to the entire center, to the entire fab division. I think it would have been a whole lot. I think we'd have worked. I think we could have gotten even more done better than we have done. Langley has had, over the years, had a really great reputation for doing things that nobody else could do. And I think we've lost that. 1283, yeah, down on Doolittle Road. They used to do a lot of pyro stuff back there. Our building at one time, part of it was underground. One building, you walk in the door, engineering's to the left, models to the right, and everything we did everything in that one building. We had 3 CNC machines in there, plus a CNC lathe, and all the tools that the machinists need, and complete wood shop in the back with the basic saws, bandsaws, joiners, planers, and all that stuff. So we could do just about anything that came up. And when it came time to put the orifice tubes in, we had a guy that did that. And it was awesome. It was a great place to work, and we got a lot of neat things done. And I'd been working in CNC work for, five years or so at that point. And I had been selected as a programmer in the model shop, and I was kind of in charge of the programming group in the building. And they had a management shift in the machine shop, and one guy retired. It's one of these things. The guy that retires, so now you got to fill that slot. Then you got to fill that slot. Then you got to fill that slot. And then you got to fill that slot. Well, one of the slots that got filled, that needed to be filled, was the programmer that was in 1283. Now got a job in the machine shop. So all of a sudden they need a programmer. So they asked me to go. It was an opportunity of a lifetime. That was a thrill working in that group. I spent most of the time with the machinists, and machinists are a different breed. But I learned things and saw things being done on a daily basis that I couldn't conceive of prior to that. The intricate setups that we required for some of the work, and the fact that they had to be repeated over and over again, because with the hard stainless steels, you can't do all the cutting from one side and then turn it over and do the cutting on the other side. You got to do a little bit on this, then you flip it over and do a little bit on the bottom, then you do a little bit more on the top, then you do a little bit more on the bottom, until you get down to where you want to be, because it'll warp, it'll distort. And these guys would take these models, and we tell them what our reference points are, and for the programming, for the CNC work, and they set it up and do the work. They turn it over, they set it up again, and they keep coming back. And when they get done, it's beautiful. Those guys, I give them a great deal of credit. I couldn't even imagine doing it, much less watch them just do it, and they do it on a daily basis. Some awesome capabilities. Favorite model? Wow. I have several, but one of my real favorites from the years was a model that came into the shop soon after I started. So I was fairly young apprentice, and I got to learn a lot about model building on this model. And it was an airplane that was developed here at Langley. It was tested here. The full scale was tested here at Langley. And I happened to, years later, was introduced to the test pilot. And I knew him as a model airplane flyer. I did not realize that he had been the test pilot for this airplane. but it was called the Tri-Service. It was an XC-142, and it was a model of a potential transport airplane, typical boxy transport type airplane, much like the fuselage of, let's say, a C-130. Cockpit up front, kind of a rectangular fuselage with a door in the tail. But this airplane had a wing that pivoted, so that the idea was to be able to rotate the wing up, rev up the 4 engines, and go vertically and take off vertically, and then rotate the wing to horizontal as they transition to level flight. And I got to build. I built the horizontal tail for that airplane, and that was fun because I got to use a lot of the neat tools. I got to use the airfoil machine, and I got to make a pattern and make a mold and lay up fiberglass skins. And I was 18 years old. This was fascinating to me, and it was a lot of fun. And it was a fairly good sized model. I guess the wingspan was about 6 or 7 feet, and the free flight model that we built weighed something like 80 pounds full up, I think. And it was big, and it was beautiful, and it was just a gorgeous airplane. And it was neat to find out later on that I hadn't actually known the pilot that flew it. But they flew it right out here in Langley, out there by the hangar. And they had you're probably familiar with control line model airplane flying. Well, they actually had a facility out behind which is now in the woods, right. But then they had like a crane, a part of a small crane, and on the arm was a cable that attached to an airplane, and they would spin the thing, and it could fly an airplane around in a circle, and they could see how the airplane responded to things. So it was kind of, I never saw that, but we kept making wheels, because we made wheels out of fiberglass for that thing. And every flight they tore up the wheels, so we had to make new wheels. And we must have made 3 dozen wheels for that airplane. Bob Champagne was our chief pilot for many years. And he passed away in 2003 on December 17th. 100th anniversary of a flight, and what a way to go, right? He was like 81 years old, 82 years old, something like that. But he was quite a guy. He probably had more hours in more airplanes than anybody that around here. He flew so many different airplanes. Some years ago, Piper built an airplane. It was a Canard airplane. They brought it here to have some of our pilots fly it for evaluation, because we had done. We're so involved with stalls and spins and spin resistance, and they had this airplane they thought was very spin resistant, so they brought it up here. And unfortunately, we lost 2 of our researchers flying this airplane because they found a problem, and they put it in the Chesapeake Bay right outside of right near Newport Light. And so we had a crash program to build a model for some wind tunnel studies. And this particular model turned out to be a real cutting edge opportunity for Langley, in that we had designers that had a lot of CAD experience, and they decided to do a concurrent design manufacture project. And rather than your typical design a model, take it to the shop, have the shop build it, they designed some overall part stuff, and then they began detailing. And as they detailed, they sent stuff to us, and we started making a model. So they were designing it as we built it, or we were building it as they designed it. And myself and another technician were assigned to do the wings. He took the left wing, I took the right wing. And the machine shop brought us a bulkhead that the wings mounted to, and they brought the spars. And we took that to a machine in the shop, and we mounted the spars to the bulkhead, handed the bulkhead to the guys that were building the airplane, and he and I took on the wings. And we were all unbelievably amazed when we put the model together just how close those two wingtips were to each other. But it was a real achievement to put that model together with different people making different parts, and the engineering was just, when you need it, they were there with the information, and it fit together and it worked, and it was a great opportunity to do things that we had never done before. I lived in Richmond at the time. I was going to high school in Highland Springs, Virginia. My dad was from Hampton, and he had a number of old school friends that were working out at NACA and eventually NASA after 1958. And they talked highly of the NASA Apprentice School, which was an educational program where you get hired to learn a trade and get paid for it, and branch at the 30 by 60 full-scale tunnel. And we built drop models, which were robust models of, at the time, Mercury and Gemini Apollo capsules, as well as usually military aircraft, fighters predominantly, that were taken over on a helicopter to Plumtree Island and dropped for spin recovery testing, and then were recovered with a parachute. And it was fun. We were doing a lot of work in balsa wood and fiberglass, mostly wood and fiberglass materials. We did very little metal work. We had engineers would bring drawings for a model, and they'd bring over periodically. They'd come other two model shops on the center that were located at the time in the west area. One was the models and plant structures, and they did a lot of inflatable things. And the other shop was the old west model shop, which derived from the old prop shop that was built back in the, I guess, 20s or 30s to build wooden propellers for wind tunnels. By 1961, it was somewhat new, but not cutting edge at the time. Those techniques had been developed probably as far back as during the war. World War II, for instance, the British built an airplane out of plywood by laminating thin layers of wood in a mold, get an education and a career. And it sounded pretty good. My family wasn't well off. I applied for college and was accepted at VPI, but I don't know, some things looked interesting at NASA. Started here in September 29th of 1961 as a dynamic model maker apprentice. And I was introduced into a small group of technicians working on really neat models of aircraft, spacecraft. We built models for the spin tunnel, which is a vertical tunnel that's used for doing spin research. We built models for the dynamic stability in the door with bags of little Ziploc bags of all kinds of various parts that they had machined and we would introduce those into the model as necessary. The group had developed techniques for doing very nice models in fiberglass, making molds, first making patterns and then making molds from the patterns, and then making a fiberglass part in the molds that they made. And in order to save weight on their models for full scale, we typically infused a dye, a blue pigment into the resin, so we didn't have to paint it, so we could save weight on paint. The shop was referred to as the dynamic model shop to separate it from the